So this is episode 13 of Prologue is Amazing. And I'm going to talk about, there's a blog post by a professor Robert Harper who I'm not sure, I can't remember which university he's at. Maybe he's at Princeton, maybe he's at CMU or something like that. And he's a professor that's interested in type theory in computer programming, and he kind of views type theory as the most important part of computer science. He also views computer science and type theory as a much bigger thing than mathematics. Right? He thinks mathematics is the actual queen of the sciences is not maths but computer science. And there have been there's a concept in computer science, the coward the Howard Curry isomorphism. I think that's what it's called. I can't remember now. Correspondence, where the types of a program is a theory, and the program or the algorithm is the proof. Right? So for in mathematics you have theorems and you have proofs. While in computer science, he says it's like there's types and then there's the algorithms that correspond to those types. And so there is a thing in computer programming called theorem provers, where you state a theory and the computer automatically finds a proof of it. Now, Prolog actually fits into this. Prolog is actually a theorem prover. Now, it's not a theorem prover of what's known as first order logic. Now, I don't understand this stuff, but it's a theorem prover of horn clauses, which is a bit of more limited than first order logic. But I'm not sure what the distinctions are, etc. But one way to think about it is like when I say Prolog is amazing because you kind of declaratively just stating your problem and Prolog solves it for you. It comes from that line of thinking where if you state, so one way you can think of it is Prolog. In a Prolog you write a theorem and then Prolog finds the proof of the theorem. Right? In other languages you're not writing the theorem, you're actually writing the proof, you're writing the algorithm. And so that's why in Prolog you're not designing algorithms, they're being found for you. And now there are other theorem provers. And so if you kind of like, there's other things like Prolog and there's now languages like Agda and Idris and things called where you write a theorem, right? You write the types, and the programming language will already automatically like calculate the thing and find it for you. There's theorem provers like that also do things like interactive theorem assistance, where you write the types of the program and it will generate a OCaml or scheme or something Haskell code or C code out of it, right? So you write a bunch of types and it generates a source code file for you that you can run, right? So now they actually have an extra thing over Prolog. In a sense, they're kind of like a typed version of Prolog, right? And maybe it's like maybe I should be doing that instead of Prolog, because it's like Prolog is, in a sense, it's like the dynamically typed version of these theorem provers. right? Because it doesn't have types. No, and there is Mercury Prolog where it has types, so you could start to think of Prolog in that direction, but you could just go to these kinds of theorem provers. One of them being COQ Coq, where you write the types and it can generate source code for you. Now, the thing he was saying was modules matter most. That's the thing I wanted to discuss. Right, so he does all his work in type theory, but in this context, he was talking about the difference between Haskell and OCaml and or standard ML. The the difference in philosophy. They seem very similar languages, and Haskell seems to be a Haskell is kind of like there was a bunch of MLs, meta languages, right, which were designed for writing theorem provers. So these languages actually developed in the seven. There were theorem provers, and then people were having a difficult time writing the theorem provers because, like, the mathematicians writing them wanted no bugs, and the languages they were using, often something like Lisp or other languages, would give them bugs, and or they couldn't be, they weren't confident that this is bug-free theorem prover. So they invented a language called meta language, ML for short, which had types. So what the types mean is that if there's a function, you state, well, what kinds of things can go here, integers or other types that you might define, and what things can come out of this. And then the compiler will check for you whether that, at compile time, whether that is the case. Like, it will look over all your code and be like, no, this, you stated that this function can only return this, but you're using it in a way where this function is using some other type. Maybe it's using a floating point number instead of an integer, or but that's the simplest kind of types. But you can define, like large types that are kind of tree structures of things, and it will check that for you. So that's why they invented ML. And then later there were a bunch of MLs, and then in the late 80s, about a decade later, people coalesced, and they wanted to develop a kind of standardized version of ML, right? Because there were MLs coming from, like Moscow ML, there was ML, Edinburgh ML, I can't remember now, but there were a bunch of different MLs from different university groups, and so they standardized on Haskell, and they added some features to ML like laziness and purity in the late 80s, and then this kept being developed until the year 2000 around about, where Glasgow Haskell became the standard implementation of this language. Now, Robert Harper and the people who were OCaml developers, they disagreed with this, that the direction Haskell went, because what it did was it thought of type classes where there's an automatic mechanism for the compiler automatically finds for you a type that might fit a chorus. It's kind of like a I'm not well versed enough to give a good description of it, and I don't tend to use type classes. But what they were saying is that that's wrong. That for the compiler to automagically find correspondence, that you probably meant this, right? Like there's occasions where the compiler will say in Haskell, you probably meant this, and it will pick something for you. But the OCaml people, like, it should never be doing that. You in your modules, you should be defining that this is what I mean precisely. You might have to write extra stuff, but you want to say in your module system what thing you mean. You don't want the compiler to probably do something, but maybe that thing is wrong. That wasn't your intention, right? And so now what he was saying is like in Haskell, the module system is not so powerful because, well, the way they added power to the module system of Haskell is by using type classes. Whereas in OCaml, the way they added power to the module system is by having like a higher ended module system, right? Like in OCaml, you can have modules, and then you can take descriptions of modules and combine up module interfaces into bigger and bigger interfaces, or hide interfaces. Like there's various ways you can combine. Like there's an entire module language. There's the OCaml language, then there's a language of the module system, and you can combine modules in different ways. In Haskell, you cannot do that. So in Haskell, basically what OCaml says most module systems are really not module systems, they're namespaces, right? So they would say like Haskell's modules are basically a namespace. It's like there's a file and you can put stuff in it, and it's just for, you can name this stuff that's in here, and you can name this stuff. Whereas OCaml's module system is a proper module system. You can have a bunch of modules, and they can be combined in various ways to create bigger and smaller modules. And then also you can already have an implementation and connect it up to modules and things. So what he says is, the article is called is about many to many, right? Modules matter most, and what he's stating is that the many to many way of connecting up modules is the right way. It's like you can put together modules in an ad hoc manner at the latest period of time that you want, right? And so, and what he's saying is that that's for the larger your program gets, the more you want this to happen. Now, in this podcast, so I've talked about how Prolog is actually a theorem prover, but it's these theorem provers like Koch and others and Idris and stuff are better because they have a types where Prolog doesn't have types. Now, a second thing is that this brings the problem, like, well, what about Prolog's module system? It's the Prolog is a simple namespace one, like you can't combine modules. And now there is a language called LogTalk where it does allow extra features. It brings features from object orientation, so you can have interfaces and you can combine interfaces. I'm not but the thing is, I'm not sure if it's as advanced as OCaml's module system, but it's also not typed, right? So an advantage of, OCaml's module system, that it's also typed. So even, you'll get compiler errors when you combine modules in the wrong ways. So, now that brings up a problem for me, is that I want to use Prolog, but the most advanced module systems are in languages like OCaml or Standard ML. And so what do I do then? So maybe it's like should I use OCaml and define up modules, the module interfaces, and then maybe they all talk to a Prolog, or maybe I need to investigate the Koch language and maybe see if it has OCaml's module system, and then maybe work in that. So I'm not sure. I have to do more research on that. But like an ideal system would be maybe something like, or maybe I would have to do OCaml and use a constraint library and do a lot of the OCaml module system, and then not work in Prolog. Or maybe I have to work in OCaml's module system and then have it talk to a database like Postgres and do the Prolog type stuff that I want, and other Prolog type stuff using a constraint library. And So maybe I need to switch away from Prolog entirely and move to OCaml, and maybe with the SQL database. So yeah, it's brought up a thorny issue for me, because there's a lot of advantages when you go to functional languages like the OCaml's module system, and then you also got the category theory. You got how defining types as unions and sums and all that, and I've done a lot of coding in that, and so it's a very fun way and very straightforward way to write down problems and do problems as well. So I've got to investigate that.